So hello everyone, thanks for coming to this conference. So here in this talk, I will introduce a mathematical model to study this question, so the evolutionary stability and the heterogeneous operation on a heterogeneous graph. So this method has been applied in these papers. So two are submitted papers and only one is published. So the last one is the rebound concentration effect and homophilic. So we will see later that this method can be applied also to magnetic scale. Okay, let's start from here. So the Friedman's lemma game. So this simplified Friedman's lemma game. So we all know this and we are familiar with it. So why this Friedman's lemma? Because in this chaos matrix, deflection is the only natural equilibrium. But of course, operation is better for the group. So we can see this. So in a group of operations, the average payoff is higher. It's B minus C. Then when we do deflection, so this D deflector is always a higher payoff because this is a benefit D, which is higher than B minus C. In this case, under the pressure of selection, finally more players can use D, and finally all population use D because D always has higher payoff than C. So in this process, we can see a declining of average rating. So this simple version of the Friedman's lemma game. So if everyone use the strategy that can optimize this payoff or limit it better, so the final result is all deflection. So this is the lowest result of the average population. So there are many ways to promote cooperation. So most here are five rules suggested by Martinova and Carsick, and unfortunately, so Carsick is not here. So I believe that we are all familiar with this, and both of them are depends on a very crucial ratio is B over C. It's a benefit to close the ratio. So this one is I will introduce in my presentation the network reciprocity. That proves that network structure can promote cooperation. So my work is based on this structure. So let's now introduce the game time graph. So we need some basic assumptions to define a game time graph. So the first one, we need to finite population, and the size of the population is fixed. So we consider a population of constant size n and distribute on a fixed graph. So we consider the graph is also fixed, not it's different from dense computation. So a player is either a operator or a deflector. So it's another assumption. And also we consider the network reciprocity, so it's not replicate population. So in our model, players only interact with their direct neighbors. So they only interact a small subset of the whole population. And also the payoff of each player is the sum of all interactions. So I know that some other models consider the payoff as the average of all interactions, but in our case we consider it the sum of all interactions. This is the second assumption. So the third one is called, it's related to updating loop. So it's the pairwise comparative updating. So I cite all these papers here because as I know, I will name this first. So the basic idea is quite simple. So in each time step, once players present randomly, for instance, in this case, this player is chosen, and then one of his neighbors is chosen, for instance, this one, and they compare their payoff. And if this player has payoff higher than this one, then this player is a higher probability we will imitate this. So this is a pairwise comparative updation. So of course we can consider this form of probability, and here is the payoff difference between this player and this player. And the omega here is the intensity of selection. So if this equals to 0, then it's the usual case. They imitate with probability 1/2, and if this is very large, this imitates the best. So this player will imitate this one only if this player has payoff higher than this. So this updating rule we consider in our paper. But of course, it's not the only updating rule. Because we all know that there are some other updating rules like first set process and last first process. So we consider it in our other papers. So in this presentation, I consider this. Okay, first to summarize some results. So some mathematical results for evolution of operation on regular graph. So this is mainly done by Austin in the paper with Martinova. So in their paper, they studied this physics. So this regular graph, The first one is cycle and the latest, and also random regular graphs. So of course they are regular graphs, but they have different structures. So here's their main results. I hope this is correct. So under weak selection, nature selection never favors cooperation under pairwise comparison. I think according to their results. So the explanation is very simple. So here is the explanation. So they showed that under weak selection, and if the graph is regular, so they found on average, the operator has one more operator. So this is the updating process, this example. And if the number of operators can increase, it means it can interact the defector. And if this defector finally imitates this operator, then the number of operators can increase. So this means this defector has a lower payoff than this one. So in their study, they showed that as a local equilibrium, so I will explain local equilibrium later. So on average, it says that the operator has one more operator among the -1 other neighbors. So this operator has already one defector neighbor. So among the other two neighbors, on average, there's one more operator neighbors than a defector. So in that case, this means in these two neighbors, the defectors, except this one, also has two neighbors. So on average, the operator has one more operative neighbor than a defector. But we know that the operator has already one defective neighbor. So on average, when we compare the payoff of this one, this operator, and this defector, the one operator has two cooperative neighbors. And the defector also has two cooperative neighbors. One is from this other two neighbors, and one is neighbor, this one. So if we compare this, and we can compare their payoff. So the payoff is this operator, he has three neighbors, so has to contribute -3c. And the second part, we get two benefits from this one and this one, from the operator. So the payoff of this operator is -3c plus 2b. And this defector do not need to contribute anything, so the payoff is 2b. You can see in this case, the defectors always have payoff higher than its operator. That's why they said that in a regular network, nature selection never favors operators under weak selection. So this is the case of regular network. Of course, in the real world, most of the real world networks are not regular, are heterogeneous. So one of the typical networks is the smallest graph. So this can generate from a regular graph, from a regular cycle, and let us reconnect some edges. So in this case, it's a small graph, and if we continue this process to add some more edges, to reconnect some more edges, then we can get a random graph. So this is a change from regular graph to random graph. And I remember that Professor Pacheco called this a single-scale network. So the variance is not very large, but it's heterogeneous. So it's not regular, so it means each layer may have different number of neighbors. So we also have another typical heterogeneous graph, which is called scale-free graph. So different from the random graph, so the variance of this scale-free graph can be very large. So we have this phenomenon. So as the population size goes to infinity, the variance of this graph also goes to infinity. So that's why it's called scale-free. So here is our topical scale-free graph. So we can see here is some hubs here. So the neighbors of this vertex is greatly larger than this neighbor. It can be very large. And we have many real samples which show that this has the scale-free distribution, like the collaboration networks, also transportation networks, computer networks, and also some biological networks. Something that everyone here are familiar with it. And also a lot of authors have studied the operation on heterogeneous graph, especially by Professor Pacheco. So in general, we know that graph heterogeneity promotes cooperation. So here is a very simple case, it's a complete graph, or it's a well-mixed population. And here are different parameter regions. And in this region, it's a Friedman lemma game, and in this region, the stack count game, or coordination game. And here is a hot dog game. And yes, I borrowed this picture from particle stator. So, and the red means full cooperation, and this dark means no cooperation. So we can see cooperation can never emerge in this region. So for instance, the gamma gate, no cooperation. And in single scale graph, like random graphs or small graphs, you can see in the small regions, cooperation can emerge. So in this region, it's the straight gamma gate, and you can see here cooperation can emerge. And also in this stack concave, you can see this line, this curve, you can see this region larger than this one. So if we add some scale to the network, in that case it may promote cooperation. And the last one is the scale-free graph, or random scale-free graph. And we can see this region becomes larger. And in this region, it's the first gamma region, we can see in a lot of parts, cooperation can emerge. So this is the main result of Archibald's paper. So this graph heterogeneity can promote. So why this can happen? So they also give an intuition in their another paper. So this is the main reason. The operators can prevail by forming a cluster, but so they can help each other, so they can have a higher average scale. The defectors are harmed by clusters. So here's a very example. So we can consider a two-star graph, and this blue is operator and defector. And if a mutation happens here, this layer is defector cannot make this top, because the top is shelf higher than its leaf. So the image can only happen here. So if this top motion to a defector, in this case, of course this defector has shelf higher than all these leaves. So as a result, all leaves will imitate this top. So all leaves turns to defectors. But if it turns defectors, then the average payoff of the top tends to decrease. And this payoff may lower than this top, a cooperative top, and this defector top. So finally, this will change to cooperation, because this can invade here, a hard payoff, and finally can go back to here. So this is basic intuition. So now I can begin to introduce our work. So we want to incorporate graph heterogeneity to the Auspicious model, because we can see this from a mathematical model to explain this. So let's now introduce our method. So in fact, we did not find any new things. So we just want to develop a mathematical model to explain all this result. So the first question is how to describe a heterogeneous graph. This is a very difficult question. In fact, a simple way is the linear matrix, but it includes too much information. So sometimes we use degree distribution, but it's also too much information, and also cluster. So in our case, we use a modified pair approximation. So this is different from the pair approximation introduced by Ospey, and we will see this later. So we focus on the frequency of pairs and use this to measure the graph heterogeneity. So the second is how to describe the updating process. We already know that we use the pair comparison updating process. So here we consider a one-step Markov process. So the updation process is not simultaneous. It's updated alternatively. So in each time step, one player is ready to update. So we can describe this by a one-step Markov process. So the third question, because here we have the condition matrix, condition probability, and the second question is how to derive the evolutionary dynamics. Because we know that from stochastic process to evolutionary dynamics is still a long distance. So here we made two more assumptions. The first one is a large population, and the second one is weak selection. Of course, it's not always necessary, but in this presentation we need this. Yesterday, we know that Zhang also introduced another model, which is the best response updating process. So it's different from this one, and in that model we don't need this weak selection. And finally, the last question, how to analyze this evolutionary dynamics? Because we have many parameters in the evolutionary process. So the final question is, if you have many equations, then we cannot analyze them. So here, because we have a weak selection, so we distinguish these parameters to fast variables and slow variables. So some change faster than the others. In that case, we can define a local equilibrium and just make this easier. Okay, here's the basic idea of our mathematical model. Okay, let's start from approximation. So the first thing is to define a heterogeneous graph. And for simplicity, we consider direct graph with symmetric interaction. So it's slightly different from many papers. Because in most of papers, we consider the undirected graph. But I will show later why we use direct graph. Because they will show that the calculation is simpler. And also we consider symmetric interaction. So this, I will show this later. So we consider a symmetric game on the graph with a symmetric interaction. There's no symmetric gradient also. And here are some notations. So for instance, we consider an n-player game, and we have the degree of vertex I and the strategy of vertex I. So basically that's this. So there are n players. So the degree of these players are K1, K2, K3. And for each player, we use this to denote the number of A neighbors in this K neighbors. The number of A neighbors into the number of B neighbors. Of course, they have K1A plus K1B to K1. And here's the pair of matrices we consider. It's a symmetric bifurcation. And here are two important terms. We'll use them later. The first one is the average degree of graph, and the second one is the variance of the degree distribution. So we use this term to measure the graph heterogeneity. So in a regular graph, we always have this variance equals 0, but in the scale-free graph, and for instance, it's very large, we have this term called infinity. Okay, here are our parameters. So let's now introduce the pair approximation for the heterogeneous graph. So here I first show the intuition of pair approximation. So it's a very old technology, and it's at the very beginning it's worked only for regular graphs. So the basic idea is like this. So they said that the conditional probability that the neighbor of an arbitrary x player is y player. So this conditional probability is derived from the frequency of pairs. So this is the very basic idea of the pair approximation. So here we introduce the new parameter. So this, because in the old pair approximation we usually introduce a parameter which is fx, is the frequency of player A or player B. But here, if the graph is heterogeneous, we need to introduce a new parameter instead of the old frequency of a strategy. So we use this parameter, phi x. So this denotes the proportion of the direct edges starts from x in the set of all direct edges. So it's the proportion of edges. So it's different from the previous one. But we know that if the graph is a regular graph, then this is exactly the frequency of strategy x. It's exactly the same. So we can see this definition. And later I will show you an example how this works. And then we have the frequency of pairs. So this are common from the approximation. We can calculate the frequency of xy pairs. And you should keep in mind that here is the direct graph. So it starts from x and it goes to y. So it's the frequency of xy pairs. And the third one is the conditional probability that x player is y player. So this is the conditional probability, also quite simple. And now we have these three terms. And we found a very interesting relation. This one. We found phi xy equals to this. So this means the frequency of xy pairs equals the frequency of x is the proportion of x edges multiplied by this conditional probability. So please notice that here is not the frequency of x players, it's the frequency of edges that start from x. So it's different from the pair approximation for a regular graph. So you may feel this very strange, but later I'll show you an example. So if you are good with this, then we have the following identities. Here in fact there are in total 8 identities, because here are some free parameters. So the first one says that each graph is either start from A or start from B. So the second is the conditional probability that the x player has A neighbors and then has B neighbors. So this equals to y self-clears. And here is from this equality. And the last one, because this directed graph, but the interaction is symmetric. So we have this phi AB equals to phi BA, which means the frequency of AB pair equals to BA pair. So let's now do an example of this approximation. So we consider this. So this is the heterogeneous graph. And here are 2 A players and 2 B players. So here we have 5 A's, but have 10 irregular features. So 3 of them are from A, is AB, the AA, AB, AB, or 3, 1. And the second 2 ones, AA, AB, AB, and also BA, BA, BA. So 10 irregular features. So then we can calculate phi A. Phi A is the direct branch start direct edges start from A. So we can do this one, this one, this one, this one, this one, this one. So this is 3 over 5. And also phi B, 4 over 5. And we can also calculate this, the frequency of AA edges, AA directed edges. You can see here, 1 over 5. And no BB edges. And the phi AB equals phi BA. And the third one is the conditional probability. Because from here we can know for each layer, layer A has 3 neighbors. One is A and 2 is B. So this conditional probability is 1 over 3. It's 1/3. And this 2/3. And then we can check this equilibrium. Okay? From here, we know here the frequency of layer A is 1/2. But if you put 1/2 here, this is not true. Because 1/2 multiplied by QAA is 1/3. You may guess this the frequency of AA pairs 1/6. This is not true. It's here. It's 1/6. So it's our new approximation for heterogeneous graph. It's different from the regular graph. So we can easily check this probabilities. Okay, with this parameters. And here in total we have 10 parameters. Phi A, phi B, and 4 conditional probabilities and 4 type of edges. So we have in total 10 parameters. And here, in fact, we have in total 8 identities. So under approximation, a heterogeneous graph can be described by 2 variables. And we use phi A and phi AA. So this method was introduced in our 2013 paper, the +1 paper. We use this approximation. So in the rest of the part, we will study our fluid dynamics based on these parameters and these parameters. And of course, we will see later if we need more parameters. And the most important thing in a heterogeneous graph, the frequency of A is not true. So this is more important than frequency of A. So this fact is very clear in a heterogeneous graph. We can imagine in a star graph, if the hub is the A player, and all leaves are B player, the frequency of A is very low. The influence of A is very, very strong. So you use this parameter, we will see phi A equals to 1/2. Okay. Equals to exactly 1.
So if you want to calculate the ratio of cooperation, then you still need the frequency of A.
We don't need that. In the evolution dynamics, we don't need that. And I will explain later why we don't need that, and we could also study the evolution process.
Okay.
Okay, now we can define the evolutionary gamma graph. So here are some tail functions. They are quite simple. For instance, if a random chosen B player and with K, and we know that KAA neighbors and KBB neighbors, then it's the tail function. And also this B neighbors. Because the B neighbors, with KAA neighbors, oh yeah, this should be A neighbors. So FA is this player's A neighbors. So we get K of A1, 2, and on average, this is the average rate, so we have on average they minus 1 other neighbors. And then here's the L function. And then we can write the transition probabilities. So here we have this one, the probability that's the change of phi A. You know phi A here is not the frequency of layer A, so the change is not 1 over n. So it's different. So if the layer has degree k, then the change of phi A is k over this. They multiply by n. This term. So what does this mean? This means if phi A is increased k, is that in this time step, we first choose the player B to update, and this player has degree k into this term. And then this player has exactly K A neighbors and K B neighbors, and this player chooses A neighbors to imitate. Only this happens, the frequency can increase like this. So that this is the probability that K A neighbors and K B neighbors, and this term is that you randomly choose A neighbors to imitate, and here's the probability of imitation. So similarly, we can write this term, the frequency of AA pair. So it's exactly the same. So based on these two probabilities, we then can write the evolutionary dynamics. So it's like this. The d phi A, so the change of phi A is the sum of all probabilities as this phi A increases, minus the probability that it decreases. Okay? And also here's the change of phi A. And under weak selections, we can do some simplifications. So it's like this. So I suppose you know how to do that, because here in the payoff we have this omega, and in the weak selection we have omega close to 0, then we can use the Taylor extension close to 0, so we can get this term. But still here are very complicated equations. And there's one more important thing, is this term. This term, if you look at the last page, you will say, so the probability of change also depends on this one. This is the frequency of B players in all K degree players. Because if the increase is exactly K, then we have to sample a K degree player. And this will have to be B. And this parameter did not appear in the pair approximation. So we need one more equation to describe the change of phi Ka. And in fact, here are many equations. Because K here is 3. So the change is like here. And under pair approximation, we also can write it in this way. And if we now look at this 3, or here are many equations in fact. If we look at this class of equations, we will see these equations and these equations. The first term are constant, are independent of omega. And in this equation, the first order term is the first order term of omega. So if we have weak selection, omega equals to 0. This means these parameters and these parameters can change faster than the first parameter. So that's why we can consider the second two, these parameters and these parameters are fast variables, and these are slow variables. So we now define the local equilibrium. So under weak selection, we found these parameters and these parameters can change faster than light. Thus, the last two equations can be substituted by the equilibrium condition. We can also always assume that the last two parameters always reach the equilibrium faster than the first parameter. So we have this condition and this condition. And if we have this one, we can solve the last two equations and get this at the local equilibrium. Of course, this depends on phi A. So what this means? This means that the local equilibrium, we have this probability that the A neighbor has the A neighbor, and the probability of a B neighbor has the A neighbor. The first probability is higher than the second probability. This means that at the local equilibrium, the K degree A players on average has this more A neighbors than a K degree B neighbors. You can see this. This is indeed the class term. Because in a scale-free graph, we know that this K can greatly larger than the minus 1. So the degree of a hub can greatly larger than the average degree. So this means at local equilibrium, A hub has many A neighbors, more A neighbors than a B hub. So it's a cluster. That's why, as pointed out by Professor Pacheco, so why in a double star graph, operator can cooperative hub help higher than effective hub. It's the local equilibrium. And with the local equilibrium condition, we can substitute all terms in the first equation by this condition. And then we can get this one, this is the global dynamics. And here we have only one parameter, phi A. But the problem here is that this dynamics is still too complicated, so we need to simplify this. So the good news is a very simple simplification. We can write this in a transform health matrix like this. So A11, 1, 2 is the standard payoff matrix. And then we add alpha here. Alpha is this one. And here also a beta. Beta is 1 plus this. And here is actually the variance of the graph. So if the graph is regular, in that case, we have this term equals 0, and beta equals to 1. And we have the new alpha. And this will go back to Oski's result, the repeated dynamics on the regular graph. And from this payoff matrix, we can get the ESS condition of specific A. The condition also quite simple. A11 greater than A21, and then R. So what's the intuition of this? So in a regular graph where the variance is 0, the condition is this one. So it's something like this one. So I borrowed the example given by Oski's paper, with this one. So at the local equilibrium, we know that except this layer, there's 2 other 8 layers. So on average, so this layer has an A neighbor, and in this 2 neighbors, one more A neighbor than this effector. So this structure at the local equilibrium is like this. So this layer has 2 same neighbors, and this has 1 same neighbor. So the payoff of this first layer, specific A is 2 A11, this one, plus A12, this. And the payoff of the second layer is like this. It's 2 A21 and 1 A22. So you can see it's exactly this condition. It's a regular graph. So what happens for a scale-free graph? When variance goes to infinity, then the ESS condition becomes this one. So what this means is this. It's a scale-free graph with average degree 3. And on average, this player has 7 neighbors in total, and in these 6 neighbors at the local equilibrium, half of them are effectors, and half of them are player B, and half of them are player A. It's the local equilibrium condition. So this becomes this one. So this is the payoff of the player A, and this is the payoff of player B. And if you let the degree of this half go to infinity, you can go back to here. So this is the intuition. Okay, so now we have a basic framework for any 2x2 symmetric game. So we can go back to the Grayson lemma game. Okay. This is a simplified Grayson lemma game, and this is the global dynamics for the Grayson lemma game. And in a regular graph, because this term, the variance equals to 0, so we didn't know that this term is always smaller than 0. So this means in a regular graph, we always have if I say dt and dt is smaller than 0. And now here we have to link EC, this phi c and the frequency of C. So at the middle point we would know. But if phi c equals to 0, we know that there's no cooperation. And if phi c equals to 1, this means full cooperation. So in this game, if we always have this one, this means this always decreases, and phi c equals to 0. This means finally there's no cooperation in the graph. So this can answer your question.
That's right.
And we found C is ESS if this is true. And we know this term is the Newman term. So C is ESS also implies that E phi c dt is greater than 0. So this will convert to full cooperation. So this is the condition. And if we check this condition, we will see this term is the right kind of this is decreasing in its variance. So this shows that in general, the variance promotes cooperation, or graph the general promotes cooperation with increases. So in a large scale for networks, we know this term goes to infinity. So these conditions became E over C greater than D minus 1, even weaker than the general rule of cooperation E over C greater than D. Let's see some simulations. We don't have no time, so I just go through the prediction and then you check the graph. So the prediction here is phi c is increasing in E over C, and the variance of K is the condition. And we run numerical simulations for the scale-free graph. And this, so this is phi c, and this exactly matches our prediction. So if we increase the benefit to closure ratio, we can see phi c increase. And here are the variance of this line larger than this line. So this means if the variance is large, then phi c is also of interest. This line is higher than this one. And we also checked the case for evolution of operation on a random network. Because the network is random, so the variance is not very large. You can see the benefit-cost ratio, the statistically is 300. So this is impossible in the real world. So that's why we cannot say operation network. That's why we cannot say single-scale network that can promote operation. But in the scale-free network, at least it's possible. And I also studied the second case. Okay, let's skip this. I just compared with subtraction of second pair means the selfish variance at the cooperative behavior. And we could also use our method to study this because this game has 3 equilibrium. But the 2 boundaries are stable, which exactly corresponds to the frequency of x and the frequency of h. But the interior difference is unclear. And here I consider the basis of attraction. So we know that in regular graph, in this game, the basis of attraction of the selfish behavior is always larger than the next well-mixed population. That means if the graph is scale-free, then the result is equal. We also have some numerical foundation. Let's show the pictures. So if we increase the variance of the degree distribution, you can simplify x. It's the sum of the cooperative behavior. You can see the frequency of cooperative behavior increases in the variance. And this is our set prediction. Okay, let's keep that. And we can go to our conclusion. So we just use 2 examples to test our set prediction. So one of the most important things in our statistical method is we do not use the frequency of the operation or the frequency of the strategy, but we introduce a new variable. With a proportion of the directed edges starts from C in the set of directed edges. We use this term to describe the evolution of C and also the evolutionary dynamics. So this is a new variable for evolutionary operation on a heterogeneous graph. And the second, from our set prediction, we know that the variance of the degree distribution plays a determinant role in the evolution of operation. So this means cooperative strategy cannot involve in regular graph if the variance is 0, but is favored by negative selection if the graph is scale-free. So why graph heterogeneity can promote cooperation? So what's the intuitive explanation? So from our set prediction is this one. K degree 6 there has on average more C neighbors than D k. So in a heterogeneous graph, the C half usually have a higher payoff than D half. So this is exactly the cluster described in the paper. And we could also answer the question which network structure promotes cooperation better. We know that many simulation results studied this question. And from our set prediction, we can show that networks with low mean degree and higher variance promote cooperation better. So therefore, it's no surprising that scale-free graph promotes cooperation better than single-scale-free graph. Okay, thank you.
I got 2 questions. One is that you probably can still calculate the frequency of a strategy using the phi c you calculated. It is possible, I think. Because in a way, it's a quantity on the network using a random picking up one edge instead of randomly picking up one node. But those 2 are dual quantities. You can actually do a transformation and then figure it out. So anyway, that's my suggestion. Second one is I see a potential of this, although this calculation, as you say, there's really nothing new, just a bunch of new mathematical analysis. Yeah. But it's possible using this we can work out or make use of the correlated degree distribution. Do you know that?
Yes, I know that.
Yeah, so the degree distribution is a bad quantity. Many structure of the network was not captured because it is counted how many K there are, right? Mm. But if you actually consider how they are correlated, like if the halves are more connected to halves, all those halves are more connected to those individual, small pieces, then there will be more information from the network gets into your equation. Usually, using mean field theory, it's impossible to do that. Yeah. But use your method, it's actually possible to take it into account those correlated distribution.
Yes, I agree with your comments. In fact, we use some mean field, at least the spirit of mean field approximation in our calculations. In that case, if there are some correlations between the degree distributions, in that case, it's maybe difficult. Yes, but we have to try that because most of our simulations are based on random graphs or random scale-free graphs.
Yes, because you're using the BA model to generate this.
Yeah.
Right? But it's not necessary. You can generate a correlated scale-free network. You can actually code the correlation in. You're using the information that one higher rank hub will connect to another hub, or one hub will connect to other smaller nodes.
Yeah, we have to try that because under these assumptions, we don't know how to simplify the evolutionary dynamics. That's also an important part. So if they are independent, we can get this dynamics.
Yes. But in principle, it's possible. Yeah.
I would just like to comment on that because I think what you say is in principle correct, but it's a correction to this. You could think of it as an expansion, and your term would be a correction term to the leading order term that he's computing.
That's right. I agree. But using the usual method that we physicists do all the time, the mean field theory, it's impossible to do that. Yeah. But with his method, it's actually possible.
Yeah.
Yeah, because he's working with the phi c.
But maybe not so useful in the mixed selection limit. But
yeah,
we have to check that.
Thanks for your wonderful talk and wonderful extension of my result. And I wonder if you have confirmed the first characteristics the third one, the difference in the number of calculators. And I remember when we did computer simulation, we have confirmed by simulation, by numerical calculation, that the calculator on average has one more calculator than a detector. And did you check that, or can you confirm
yes,
that
in
simulation?
Because you test that in a random graph. Because a random graph, the variance is not very large, so on average that's true. We tested in the scale-free graph, the variance is very, very large, and we found this is true.
Thank you for your excellent presentation. My question is about you have cited a reference which written by Santos in 2005 and published in PIL. That page says that scale-free network facilitated cooperation a lot, but what he used to calculate the payoff and the updating rules is just only one method. He haven't considered about another method to calculate the payoff. You use the accumulate payoff here and the fin form updating rule, right?
Yes.
And I remember Santos have written a paper in physical reports said that scale-free network maybe is not the only reason that can facilitate the cooperation, because if you test different kind of method to calculate the payoff, for example, the average payoff. So you accumulate the payoff and divided by the labors of the individual, or you choose another updating rule. Let's influence the result a lot, and the scale-free network doesn't facilitate the cooperation. So you just use the same method as the paper of Santos. I think that cannot be explained that the scale-free network does facilitate the cooperation?
Thanks for your question. In fact, we tried different updating rules in other papers, but some of them are unpublished yet. So we published one is based on best first updating, and yesterday Zhigang presentation is based on best response dynamics. Yes, exactly, we have the different updating process. But some of them are unpublished yet, so we have no time to presentate here.
So the results is robust according to the different updating rules and the way of calculating the payoff.
Academics in general, scale-free networks promote cooperation better than the others. We test 3 or 4 different updating rules and found this result. But it's more because I use it. That's first. I use imitation updating in this presentation because most of you are familiar with it. But most physicists are like this much better, and the methodologist is more like best first updating or some other model process, and the economists they like best response process. But in this presentation, I just use the pair comparison. In fact, we did our updating process.
Okay, thank you.
Okay, I have a simple question. Thank you for your nice presentation. And after the Osuki's work on the evolution of cooperation in the regular structure population with pairwise interactions, and there is another work published in JTB 2011, and the author is also from Japan, and I remember that he considered the heterogeneous population structure, but in his paper he used the linear fitness mapping from the pair of the individual got it from the game. I'm not sure whether you have read their paper, but in this paper you consider the Fermi process during the calculations as to the weak selection. You will want to go on the calculations with many the Taylor explanations. Yeah. But for your paper and that paper published in JTB in 2011, no matter what you consider the linear mapping or the exponential functions, after the Taylor explanations, we get the same expressions. So what do you think of your innovations about the work since another work have already done before?
In fact, we know that paper, and I remember that in their paper you consider the distribution of pairs neighbors.
Yeah.
And but you know that it's a local chapter. Okay.
Yeah, but I think in that paper maybe consider a wider situation than you have done. Maybe. I'm not sure whether you have read.
Yes, I know that paper.
Okay, thank you.
Okay, let's discuss
the letter. Okay, now and the coffee time, and I think and 5 minutes, and I think. Oh, thank you.